ALU. Okay, it is called arithmetic logic unit or arithmetic and Boolean logic unit. Okay, also there are some registers. Okay, so there is PC, there is IR, there is status flag. Okay, and also without this so along with this ALU, there are some other processing block, that is it will perform very a specific task, very specific task. For example, it could be adder other than this ALU. Okay, or it could be shifter, it could be complementer. Okay, so these are the very basic operation other than ALU. ALU is basically used for what complex mathematical operations. Okay, or if this ALU is so basic, if ALU is primary one, then these things will be included inside, they will be placed inside. Or if ALU is more complex, then other than this ALU, these blocks will be separate out. Okay, then there is another unit, it is called control unit. Okay, okay, so one thing I could rectify the figure like this. Here one portion could be dedicated for adder, and the portion could be dedicated for shifter, and the for complement, and other will be the complexes. Okay, this is the ALU part, it is the registered part, it is the internal bus, and this CU. All of them are connected.
Sir, I think a few students might be in the waiting room.
There is no waiting room. I have disabled the waiting room.
A lot of students are saying that they cannot enter.
I think at that case they are using previous my older connect link. I have updated the link.
Okay, sir.
Okay, so we have discussed about a functionalities of processor, internal picture of processor, and within this processor there are these three components: registers, ALU, components, and they are connected with this internal bus. Okay. So if we discuss them one by one, the first one could be registers. Let me say in another way, they are the internal memory of processor. Okay. They could be divided into two ways. One is named as user visible register. Another is control and status register. And from this name, it is evident that this register will not be accessible for users or for programmers. Okay, that means it is privileged registers or authorized registers only used by OS and processors. Okay, and these user visible registers are used by the programmers and users. Okay. Okay, there are some other type of registers. They could be used for both. For example, PC, program counter. Okay, so it is another kind of register that could be active as this both types. Both types. The PC could be used as user visible register and also acted as control and status register. That means your OS could change this PC. Also, user visible user data or user program could access this PC. and others could be flags. That is when you are performing any arithmetic operation, Boolean operation, so your status registers are changed. And what are the statuses? For example, sign. Sign is one kind of status. It could be positive sign, it could be negative sign. So what is a sign? After performing the very last execution, then sign flag could be changed. Okay, and this sign flag could be your user visible register. Also, it could be your control register. So this is the internal memory of processor. And from the memory hierarchy, we have learned that the registers are so small in size, but very fast in speed. And why it is so speed? Because it is inside the processor, and their technology is similar to the architecture of or technology of processor. Okay. Do you have any question? Okay. If you don't have any other question, then I could differentiate this category, this type user visible registers into further types. Okay, so they are categorized as, sorry, please. This user visible register is categorized as also general purpose register. Okay. If I make it more specific, it could be data register, it could be address register. Okay, and also it could be condition, codes, or you can say flags. And main feature of user visible register is that programmer and user could access this type of registers. They could view what is the content of these registers. Okay. Now, this general purpose register could be generalized. That means that they could be used for any kind of instruction, or they could be instruction specific. Okay. So we will discuss this thing later. But as very beginning, I could give the give its explanation that this general purpose register could be used in two different ways. It could be more generalized, that any kind of instruction could use them, or there are some specific examples. Specific examples. I will show this thing in the next slide. That how these registers, generalized register, could be used for a specific purpose. Okay, so these two registers are so specific, comprehensive. That is they how they are used. One could be used for storing data, and the address register will store what different kind of addresses. Okay, so only we have learned about memory location in different chapters. Also, it is okay, all the addresses are prominently used from memory. Also, it could be used to locate your registers. You know, there are different registers inside your processor. Okay, so if you specify a particular register, of course you need to know its address, register address. Okay, and inside your memory, we have discussed there are different segments. There could have core segment, there could have data segment, stack segment. Okay, different pointers could be there. 2 points defined prominent information. For example, page table. For example, interrupt vector. Okay, it could be index. So these things are very special addresses from your main memory. Okay, these addresses are coming from your main memory. As they are so prominent, so significant, so your processor should know them, and it should be stored. These addresses should be stored in a very prominent places. and these places are registers. Okay, so some registers are there to serve this purpose. That is, say they would store specific addresses from main memory. Okay, and when these addresses are used, obviously there are defined modes of addressing. There are three defined modes which are connected with the register. One is register addressing mode, register indirect addressing mode, and displacement addressing mode. Okay, so these are the three types where your registers are involved, and at that time you should know particular which mode is involved here to specify your address. And the fourth one is conditional codes or flags. And when you are performing any kind of operation, so this operation basically changes the environment of your processor, and this environment basically reflected by your flags or status. Okay, and these flags basically mention, okay, what was the type of the last operation. Okay, I have already shown one example, sign. Okay, also there could have overflow. Okay, like this, also interrupt. So there are different flags are there. Okay, uh, what is the current status that should be reflected through these flags. Okay, do you have any question up to this point? Like I said, there are different kind of registers. They are acted as internal memory inside your processor. Different types of user visible registers. Another type of register is control and status register. Okay, if there's no other question, I would add some more information regarding user visible register. For example, how many registers are there? How many registers are there? Okay, the optimum number is 8 to 32. 8 to 32 registers are there in a system. So how do you think? How many bits will be required to mention them separately?
5.
5 at most, 3 minimum, isn't it? So inside your instruction, only 3 bits in minimum or 5 bits at maximum required to mention the register address. Okay, and if you include this register address, it is basically saving memory access. What is time consuming? So what do you think? So should I accommodate more and more registers? So my point was, if I add a register address inside the instruction, that is basically saving my memory access. And memory access basically time consuming event. Memory access is time consuming event. So when I am avoiding this part using register address, so it is basically what? Taking less time to perform my operation. So is it logical that I should accommodate more and more registers inside the processor? So after 32, it could be 64 or 128. That many registers will be added inside the register, inside the processor. What do you think? Okay, theoretically, it is sound. Okay, if I add more and more registers, then I could save time. But practically, so when the survey was worked, they have found, so 32 is the maximum number to get the maximum speed up. So after that, if you increase the number of registers, so the speed up was what? It is reducing. Okay, so from this experiment, you could decide, okay, 32 is the best number of registers to be accommodated inside the processor. Okay. And another question, what would be the length of the register? Length of register. So, okay, so we have heard 8 bits, 1 byte. It could be 16 bit, it could be 32 bit, it could be 64 bit. So based on the architecture, your register would follow a particular length of register. The thing is that when your register is using 16-bit raised 16-bit length, also it could accommodate 8, because 8 is automatically convenient for this type of architecture. Similarly, when it is 32, also it will support 16 and 8. When it is supporting 64, it also supports 32 and 16 and 8. Okay. Now, there are at most 32 registers. They could be generalized or they could be specific. Now, when it is generalized, so how many bits will be required? We have seen 5 bits are required. When it is specific, that means I would make them category. Okay, I will use 8 registers for this purpose, for a particular task, 3 registers for this task, 3 registers for this task, and what? And 2 registers for this task. Now, what do you think? The number of bits inside the instruction reduced or it is same? Because here it was 5 at most. For this specific type of registers, what do you think? How many bits to be required? So when you have made it specific, so for 8 registers, only 3 bits is enough. For 3, 2 bits is enough. For 3, 2 bits is enough. For 2, 1 bit is enough. The thing is that when your opcode is specific, then the number of bits inside the address field, it could be reduced. That is, you are saving bits inside the instruction. Okay, making your registers specific to a particular opcode. Thing is that when you make it specific, so number of instructions could be what? Excused. Okay, that means one kind of trade-off. That means you are decreasing the number of bits, but the thing is that your opcode should be more specific. And when your specific means what? You have to add mode. What is the type? Here I have given 4 types. So among these 4 modes, so which mode you are using, that mode you should specify to find out, okay, in which way you are using this address register. Okay, but if you use 5 bits to address a particular register, then okay, at most I have 32 registers, so I could accommodate 5 bits to address any register, so I could go to any location. Okay, but thing is that it is 8, that means only 3 bits I can use. But which 3 or which 8? 3 bits means what? 8 registers, but I have in total 32 registers, but which 8? So this indication will be done by this mode bit. So also you have to add mode information with this specification mode. Okay, so that is one kind of trade-off. So you are saving this in one way, but you have to sacrifice in another way. Is it clear? Do you have any question? Okay, also one thing that you should know, that when you are performing context switching, you know what is context switching. Could you give an example where this context switching could be happened?
Yes.
Sorry. For example, when you are calling procedure, function call, also it could be interrupt. Okay, like this way, when your processor is switching from one program to another program, so context switching will happen. For this context switching, you have to store these user visible registers. Okay, so it is a part of your context. Okay, so next one is, we have already discussed about user visible registers. So one is remaining, that is control and what? Status register. Okay, so very common control register is PC, is also used as user visible register. And what is the purpose of PC? It is indicating the address of next instruction. Also, there is IR, that is holding the current instruction being executed. Then MAR, holding the memory address to read any data, to write any data. Then MBR, okay, IOAR, IOBR. Okay, so they are control and status register. They are not accessed by the user. So these registers are directly accessed by the ALU to perform any kind of operation. It could fetch data or store data, or it could decode instruction, it could fetch instruction. Okay, so these could be processed by ALU, could be processed by ALU. Then at that time, ALU could access them. Okay, next one is status registers or flag registers. So in formal way, they are called program status flags or words. Program status word. And in short, it is called PSW. Okay, or another name is flags. So example of flags is, I have already said, sign flag, then zero flag, carry flag, then equal flag, overflow flag, interrupt, disabled or enable flag. Okay, so these are the prominent flags that is reflecting the current status of the processor. Also, there are some other control register. For example, PCB. What is PCB? Do you know? What is interrupt vector? What is a stack? What is base table? Have you heard those terms earlier? PCB, interrupt vector, stack, base table. PCB is basically process control block. Interrupt vector is one kind of table that is holding interrupt address, so interrupt name or interrupt ID and its corresponding address, where it is stored in your main memory. So interrupt vector is kind of mapping table. So similar to the page table, where there are different pages under a particular process and their frame number. So it is another kind of mapping table. And a stack is one kind of data structure to store your temporary data. Okay, so it is also placed inside the main memory. So all these things are stored in your main memory, PCB including. So in your main memory, where they are stored, so those information, those addresses will be set or placed in these registers. Okay, there are some specific registers where this kind of addresses will be stored so that your processor could readily access them. Do you have any question? Okay, if not, I would show you one figure. Is it visible, this figure? Could you see it?
Yes, sir.
There are two microprocessors. One is Motorola MC68000 32-bit microprocessor, and that's Intel 8086 16-bit microprocessor. Here I can see these registers are divided into two ways for general purpose. It is general purpose data register, address register, and it is control and status register, and it is program counter. All of them, or maximum of them, are what? 32 bits, only status plus is 16 bits. And there are 8 data register and 8 address registers. Now, when we will look at 8086, all of them are 16-bit register. So it is user visible. Okay. So other 3, they are what? Control and status register. Okay, only visible by the OS. So here you can see it is AX, BX, CX, DX. So 4 user visible register. The thing is that they are also specific to a particular task. AX is used for accumulator. BX could be used for base register. CS could be used for counting. DX used for data. Okay. Other than this general purpose register, they have some specific task as well, and when it will be specified inside the instruction with a particular mode. Now, when we look at OS-based registers, that is where OS or processor only could access those registers. You can see it is a status registers, flags, and it is PC instruction pointer. Other than that, these 8, they are basically used for segmentation. I have already discussed about segmentation in OS. There are different segments where first address will be stored in register, and then where your desired data is located, that could be specified with offset. So here you can see, so they are your starting address of different segments, and they are your offset. So if you know your stack segment and your stack pointer, so if it is a stack segment, starting address is mentioned in this segment address, and your offset, where it is stored. Okay, what is the distance from the starting address? So it is mentioned in this stack pointer. If you add them, you could find out the exact location. Okay, so with these 2 groups, you could find out the location of exact location of your data desired information easily. Do you have any question? Okay, if not, I could show you another architecture. It is a little bit similar. It is 16-bit, it is 32-bit, it is also 32-bit, but it is extended from 8086. It is called 80386, and here it is 32-bit. AX, BX, CS, DX, they are now extended by another 16-bit. So in total it is 32. SP, BP, stack pointer, base pointer, stack, source index, destination index, they are also increased. Okay, so it is your flag register, it is your instruction pointer or PC, program counter. Do you have any question? Okay, so you know instruction cycle. So what is the first step in your instruction cycle? What is the first state of your instruction cycle?
Instruction
Instruction what?
state.
Huh? Instruction address calculation. That is the where your address is stored, that address should be calculated at first. Then it will be fetched. Then what? Decode the instruction. If you need any operands, okay, operand address should be calculated, then operand should be fetched. Then you should perform data operation. Then if your result should be stored, again your operand address should be calculated, then your result will be stored. Then what? Then what? You have to check the interrupt. If there's an interrupt, you have to solve the interrupt. Then again you have to check the next instruction address. So have you remembered this thing? Do you know this thing? Okay, so now thing is that if your opponent, your opponent is using an addressing mode that is not indicating the effective address exactly. That is, this address is not actual address where is your data or information. That means it is one kind of indirect address. And when you follow this address, then you will get another address. Then if it is the last address, final address, okay, then you could get your operand. So indirect addressing mode is there so that you could use the navigation of different addresses to find out your actual operand. Okay. What do you think when these indirections happened? Does it take less time or it will take more time to complete your instruction execution? Will it take more time or less time using addressing indirect addressing mode? Okay, so basically it will take more time. Why? Because it for indirection it will access memory multiple times. Access main memory multiple times. Okay, so this operand fetching and string operand will access your main memory multiple times to find out the exact location. Okay, indirect. Okay, so it is another kind of stage. Okay, I could say it is a separate stage. It is a separate stage where you have to access your main memory multiple times to find out the actual operand other than these states or steps in your instruction cycle. Okay, So now we will add this stage with this instruction cycle. Okay. Then it will look like this one. Okay. So here it is indicating that this stage or this step will require more memory access, and it will basically increase your execution time. Okay. Previously, you have seen only fetch was there, then it could execute. After fetching the instruction, it would execute the instruction. Okay. Then again jump to the another fetch instruction, then execute that one as well. Then we have added what? Sorry. Then we have added interrupt. Okay. After performing execution, we will check if there is any interrupt or not. If it is, then after performing this interrupt service, then it will go to the next instruction fetching. But now we have another stage. It is called indirect addressing or indirect memory access. Indirect memory access. After fetching the instruction, then when it is found, when it is done, then it will go to the execute operation. Okay. So this figure is basically elaborated in this state diagram. Is it clear? Or do you have a question? Okay. Now, another topic is data flow. Data flow. Okay, what is data flow? Basically, when you are fetching instruction, fetching your operand, execute that one, find the result, storing that one. So basically, your data or information is traversing from one register to another register, isn't it? From is for example, from MAR or MBR to IR, IBR, then okay, what MAC. Okay, like this way, in different registers, your data is moving, isn't it? So in which sequence? In which sequence your data is traversing? That is called what? Data flow. Okay. If I show one picture, if you have any question, you could ask me. That means, is this figure understandable or not? This one kind of timing diagram. Timing diagram. Okay. What can I see in this timing diagram? That your first 4 time cycles, it is performing what? Fetching opcode or instruction. And here, these data bus are used. Then you are using this command. Okay. Also, it is input operation or memory operation. It is indicated by this one. Also, you could give another signals. So through S0 and S1. After fetching the instruction, you could perform memory read operation. T5 to T7. Okay, within this time, after this time, execution will be finished. Then after that one, T8 to T10, your memory writing the result will be performed. Okay, in this way, how the information will be changed, that will be depicted through this timing diagram. Similar thing I could show you through another figure. It is called architecture figure. Architectural figure or architectural design. So how they are what sequenced, or how an instruction could be executed in sequential manner. So from this figure, it will be easier to understand. Okay, how? So the what is the first step? It is instruction fetch. So from where I could get the address of instruction? From the PC. So from the PC, when I could get the address, I will go to the instruction memory and I will fetch it and store it in the IR. simultaneously I will add minimum value to address the next instruction. So adder will be there. So it is your next PC. So when it is in IR, so now it will find out, okay, which operation will be performed. So that will be performed the ALU, okay, which values will be required to perform this operation, that will be fetched from this register and stored in A and B this portion, and they will be sent to the ALU to perform. Then it is your ALU output. Then it is what? Memory write operation. Okay, so it is one kind of sequence, isn't it? So it is called data flow diagram in two different ways. Okay. So it is very complex one. So I could show you very basic one. What is the basic one? Okay, this one. What is that? It is only phase part, phase cycle, fetching an instruction. So what is required? So you should know what is the address of the next instruction. That could be stored in PC. Okay, so PC is indicating location in which place. Of course, it is main memory. So somehow I have to access this main memory. So through what? Through this system bus, isn't it? So how could I access this system bus? Through this MER, memory address register. And memory address register will send this address to where? To address bus. Okay, address bus is holding the address of main memory. But so what is the command to this memory? Who will give the command? Okay, your control unit will give the command. Which command? Read command. So read command will be sent to the control bus, and from this control bus, you read command to the main memory. And when it is a read command, so your data will be sent to the CPU. Data will be sent to the CPU. How? So first task will be, it will be sent to the data bus. Then from the data bus, it will be stored or copied to the MBR. Okay, and it is what? Fetching cycle, and it is fetching what? Instruction. So now it will be stored in I. Is it clear? Do you have any question? Okay, so another data flow could be your indirect cycle. Okay, make it more familiar. So interrupt cycle is another familiar event. Okay, so how it will be done? So interrupt means what? Context switching, isn't it? That means you have to change your current environment. So what are the current environments? Okay, very prominent current environment is PC. PC should be stored in your main memory in a particular stack. Okay, the PC value should be stored. So where it should be passed at first. It will be sent to the MBR because now it is data. Now it is not address. It is your data. So this data should be stored in your MBR and then to the memory. But how can I send it to the memory? Okay, obviously using the system bus. So at first it should be sent to the data bus. So it is sending. That means it is which command? Write command. So who will give this command? Your control unit, isn't it? So that control command, write command will be sent to the control bus. Then from this control bus, it will send to the main memory. Then that data from MBR PC content will be stored in your main memory. It could be stack. Okay. Oh, one thing. It is write operation, isn't it? So why it will write? Why will it write? It will write in this stack, isn't it? So what is the address of this stack? Okay, that address should be known to the control unit. So control unit will send this address to the MER, and MER will give this address to the address bus, and from this address bus, it will be sent to the main memory, and from the data bus, your PC address will be sent to the main memory. Now, so one part is done. So what is the current information that is saved now inside your main memory? Another part is remaining. What is that? When you're performing interrupt. Could you hear me? So when you are performing interrupt, one part is my current information should be stored in main memory. What is the next part? Okay, my next part is I should know the address of IH. What is IH? Interrupt handler, or you can say ISR, inter service routing. So why is it stored? It is stored in your main memory. Where? So that address will be known to the control unit. So control unit now send the address of ISR, and that address will be stored in PC. And you know what is the task of PC? PC is basically indicating the address of the next instruction. Okay, and following this PC, your processor will fetch your next instruction, decode it, fetching your next operands, okay, required operands, execute them, extract the result. Like this way, the cycle will go. Okay, now what is the remaining? That is indirect cycle. So what is indirect cycle? That you are using the instruction address field to locate another address of your main memory. So you are fetching your instruction from main memory. So fetch instruction is stored in your MBR. And you know, from this instruction, you write that many bits. For example, Y number of bits will be used as what? Another location inside the main memory. So that many bits will be sent to the main memory to access another location to find out your actual operand. So which operation is it? It is read operation. So control unit will give the read command to the control bus. What is the address? So the MAR. Okay, and after performing this read operation, your a memory will send your data to the data bus, and from data bus it will be sent to the MBR. If there is another level of interaction, again the same cycle will be happening. Okay, now if I am asked, okay, what is the data flow for different operations, execute cycles? Okay, in that case, I cannot make any generalized format like this. Okay, because the operations are different and they have different sub steps as well. For example, it will move data, transparent data, it will perform some memory access, for example, read or write operation, and also it will access your ALU. It will perform your operations through ALU, and it will exchange data with memory. Okay, that it is data transfer. And also, if there are some registers holding some data, also it will fetch data from these registers. Okay. So in this way, I could make different flow diagram. That is the execution of different operations. For example, we have already discussed indirect operation, indirect cycle, phase cycle, interrupt cycle. So these events could be expressed in sequence, data flow. Okay, so these are things that how your processor is designed. Processors have different components, different registers, different sections in your ALU, control unit. Okay, how they are connected in sequence to perform a particular task. So that is now mentioned. Okay. Okay. So do you have any other question? So if not, then that's all for today. So see you in the next class. So you can leave now.
Assalamualaikum, sir.
Assalamualaikum.